This is not a reaction video. I'm not gonna redo this blog out loud. I'm just gonna use it as a motivating factor to talk about something I really dislike about Unix-like operating systems. You saw the video title, it's environment variables. So why is Rust sad? Why it didn't save us? And what is so not thread safe in cstdlib? If we scroll a little bit further down, we see that there was a crash, and crash happened in getenv. And how is it even possible to crash in getenv? So today we are going to dive really deep into how environment variables work on Linux, how they get passed into your program, why they are so bad, and maybe some advice on how to deal with them. All right, let's switch to the code view and do some exploration. And we start with your regular main program that accepts argument count, arguments, which is char star to array, argv. And also, if you saw my Sleep from Scratch video, there is another array of environment variables that is passed from the stack pointer. And we are going to print all of them. So let's have some index that is 0 and just print all of the environment variables in the loop if I can type today, and MVP index equals 0 because this array ends with a null terminator. Always, always, always. We'll just print f, which is a string, index. Yeah, so let's just print all of the environment variables, and at the end we need to increment the index. And after we are done, we are going to print, and I keep typing print because I don't normally write C, count of our variables, the amount of variables. I think that should be it. And if we gcc env, I screwed it up. Oh yeah, because I forgot to include the header. Include stdio.h, and I think that should be it. Yeah. And if I press env, yes, I indeed get all of the environment variables. I surely hope there is nothing secret here. I'm gonna edit it out if there's something secret. And I have a count which is 40. And let me double check that I didn't screw anything up. I'll just actually rerun it into env.txt and make sure that it's actually 40 of them. And you don't see it actually. Yeah, actually you don't see it behind my head. So let me just show you. It is, you see 40 lines. So we indeed have 40 environment variables. So this is all working. And just to double check, let's run env, so that regular env that prints all the environment variables, and pipe it through this wc-l, and yes, so I did it all correctly. Now let's add a new variable, and we need to include another header, std lib.h, which has setenv, which accepts 3 different parameters: name, value, and whether to override or not. So let's call it a new var. Let's set like, I don't know, high and false. We don't care about that. After we are done, let's set index back to 0 and do this all again. Let's just enumerate all of the environment variables. We don't actually, let's not print them anymore. Let's just call this count2 and call this count1. And let's recompile and rerun it. And wouldn't you look at that, both of them show the count being 40, even though we supposedly added something new. So what is going on here? Let's try to get env this variable and see if it exists at all. Maybe we screwed something up. So let's just get env a new var and call it char star new, and me just flexing on C++ people that I can use this as a variable. So yeah, let's print it out and see if it exists. And yeah, it is print f, the very common mistake that I make when writing C. And it actually exists. So what is going on? And let's even print variable the second time again, just so we absolutely make sure. Let's do env.txt, then let's open the env, and we have 40, we have high and new. So there is not new var here, nowhere to be found. So what is going on? Before we go any further, let's just sit and think about it. We get environment variables on the stack from the stack pointer, but then we call in setenv and add something there. It kind of seems odd. Everything we have on the stack, like arrays, they shouldn't be just expanded. This is not how stack memory works normally. We don't talk about things like alloc A. So something else is going on here. And I think in order to figure it out, we need to go to the source. And when I say to the source, I of course mean glibc source, which I have over here. From the sleep video that I'm gonna link in the description, we know that we need to find a start entry point that is written in assembly. And here we see that it's source EBP, and somewhere down below it aligns the stack pointer. Basically, it follows the MD64 ABI, and it pops argv argument count, and somewhere down below it calls, no, this is not it, yeah, it calls main that is in C. And if we go, here it is, to libc start, a little bit down below, and yes, you can see that this is glibc, all right, the one we love. Somewhere here it should be doing, I think it's EV. Yes, there you go. So we have libc start main, and here's our environment variables, and they get it from argv, so they get address on argv. Just add one to that, and they know that environment array follows arguments. It's like right after, so they get that. And after that, they assign it to some variable named underscore underscore environ. Okay, so what it is. And so let's go back to our own program and let's try to experiment with this variable. Let's see if we can even access it. Oh, and before we do, let's actually see where it is defined. So I just know for a fact that if we go to this uni.std header and we search for it and we run environ, yeah, here it is. So here it is defined, and there's even a version without underscore if you have some kind of if def. But yeah, that's the header. So let's go back to our file and include that header. It's uni.std.h. And I guess instead of using NVP the second time, let's try to do environ. And this is supposed to just work, I guess. So let's quit new Vim. Let's clear the terminal. Let's recompile and let's rerun this again. Open new Vim back, and wouldn't you look at that? Now we have 41 environment variables, and our new var is right here, and it equals high, just as we would expect it. And so let's just step back for a second and think about it. We got our environment variables as a pointer to an array, and it's allocated somewhere on the stack. And then we copied that pointer into some global variable that is entirely managed by the library. And then getenv and setenv, they just operate on that global variable. And now you can easily imagine why this crash happened. So something calls setenv, and initial array doesn't cut it. So the libc actually allocates a new array, copies everything there, and puts a new variable over there, and then switches the pointer to a new thing. After that, you call getenv somewhere, and then what happens is that another thread calls setenv, and that array might have to grow again. And when dynamic array grows in C, what will happen is that you have to call realloc, which will allocate a new array, copy everything there, and then point this global variable back to it. But you get this race condition when getenv actually gets a pointer to an old memory, to an old pointer that is invalid now, and then this pointer gets dereferenced and you get a crash. So yes, and this is exactly what happened in this article that I'm gonna again link in the description. And just think about it. These two little functions, they absolutely must just working with global variables from multiple threads that are, you know, barely synchronized, I guess, if it's so easy to crash. If you read this article up to the very end, they will mention some kind of a fix. And the fix is that Glibc project has also very recently added more thread safety to getenv. Let's look exactly how they implemented it. So let's go back to Glibc and let's find, oh, I copied something here. Let's find getenv.c. So there, yeah, there you go. And let's look at getenv here. And it actually starts with an infinite loop, how scary. And then, let me actually, I guess, expand Emacs. It loads some kind of a start counter from environ counter. That's very interesting. And well, this procedure has a lot of comments and not much code, but I think we can't really understand what's going on before looking at Setenv first. So let's do that. So let's go to Setenv and check it out. And after a bunch of jumble of defines, because of course it is glibc after all, where is Setenv? There you go. So there's our Setenv and what it does, a bit of a validation. And after that, it calls add to environ, which is here. And this, I think, where everything interesting starts. Yeah, here is our global variable, double underscore environ. So we get its address and we are taking it atomically. And so loading it atomically just means that it's either loaded or not. There is no some kind of a weird like intermediate state where a pointer is like half loaded. And so we get it into a start environ, then we assign it to this EP, and after that we have some kind of a result environ. And then we try to find the name of the environment variable we are trying to set. So we either find it or we reach the end. And this is the branch that interests us when we actually fail to find it. So we have to add a new environment variable. This is what's gonna trigger our like scary condition. And in the first branch here, we determine that required size is less than whatever is allocated on the environ array list. And by the way, what is an environ array list? Let's actually check this out. It's actually in getenv.h. I don't think I have it open. Not setenv.h. Yeah, there you go. So the environ array list is a global. It is a global. Is this? Yeah, this is it. This is the environ array list, and it has a type of environ array. So which is a struct that has a pointer to an actual array of envs. It has an amount of allocated entries, and then it has a pointer to the next environment array in the chain, which is named a little bit confusingly because it is actually a previously used environment array. So this is your dynamic array in C101. Well, it's like dynamic array plus linked list. And so what happens is that it checks this global array list, which always supposed to point to the currently used array. It checks if it has enough allocated space here. And if it does, we're all good. We assign null to the very end of the new end of the array, and then it goes all the way back and it calls mem copy of a new name, new value, and the equal sign. Then we happily return. This is not that interesting. The most interesting branch is this one, where we cannot use environ as is and need to copy over all of the contents into a new array. And so what happens here is that blah blah where it is. So existing array has enough room, content is copied below, we don't care about that. Yeah, so here, where we allocating a new array. So there is a helper procedure called environ new array. It is in the same file here above. If you ever seen dynamic array in C, you know what it is. It gets a new size that is, you know, like a little bit more than existing size. It zero initializes a new array that gets put like over here into a new environ array. After that, it initializes new, like an outer struct, so the container struct, I guess, and then it sets new size, then it sets a new array, like that we zeroed out, and then it adds like a previous array list that was current to the next, which again, next actually means previous. And so we have this chain of arrays that filled with like stale environment variables. So I think at this point you kind of see where we are going. And so let's go back to our Setenv here, where we allocated a new array, rearranged the chain, and then on a target array, what we do is we copy all of the contents of existing environment variables there, so it's, you know, accessible. So I guess getenv doesn't have to do all of this chain walk. It can just use whatever is on the environment array list. And after that, we go down and proceed with mem copying the new value. So again, to reiterate, there is a global variable that holds an array list, and it is list of these structures, which are dynamic arrays that stores amount of allocated entries and also links to all the previously used arrays. So these previously used arrays, they, as you can see, they are never freed. So they are leaked. And then we store our result environ that now points to the current array into our global double underscore environ. And so when we go back to getenv, this is it. Yeah, we can just access it. So here the getenv just accesses environ directly without having to do any sort of, you know, like weird walk. And then it just tries to find the value, and then if it finds it, it returns it. But getenv actually has a lot more to it than just finding an entry after setenv. It also handles unsetenv in a completely different way. And if you look at it, it loads some kind of environ counter that's used to deal with concurrent unsetenv. And at the very end, it has this huge block with a big comment. So like what happens here? And basically, if we go back to setenv and look at unsetenv, then what it does, it also has like a loop that if it finds the environment variable it needs to unsetenv, it removes the pointer by moving everything later back. So it doesn't leave a hole. It actually always has a free space at the end. And it does it again atomically. And somewhere in the middle, it does like releases, and it does these releases to synchronize with acquire loads in getenv. So just like this is such like a complicated code that in order to, you know, like fully understand it and fully like know what's going on, you literally need to go through all of this, and it's actually pretty well explained. I'm not gonna read it out loud. If you're interested, just go and look at libc, like glibc source yourself. It's actually very educational. Like glibc, I know it has this reputation on written in a very like super horrible way. And it is all true. The allegations are true. If you followed me here, you've noticed it yourself. But it also has a lot of comments that really help you to understand it. So, yeah, I hope this was interesting to look into, how this very simple getenv, setenv, unsetenv interfaces can hide this very like complicated and involved logic. Again, going back to this article, right? This glibc added more thread safety by leaking older environments. So it used to crash, and now instead of crashing, your application will get potentially a stale value of an environment, which is better. I guess it's for you to decide. After all you've learned, is it really worth it? In my opinion, absolutely not. I think you should put a big effort to avoid using environment variables as far as you can go. They are completely unstructured. It's all just some character strings that can contain absolutely anything. It is global and mutable. Anything can set them, anything can get them through an exposed libc interface. It's also very inconsistently implemented, so glibc, as we found out, goes completely out of its way to at least not crash your program. But first, it is a really recent addition. It's March 2025, so there's a lot of server with old glibc versions, a lot of desktop computers with old glibc version without this addition. And we are not even talking about libc on Windows or like FreeBSD or whatever else. So instead, I think you should use literally anything else. So it could be config files, it could be systemd units, like pre-configured ones, it could be command line arguments, GUIs, web dashboards. Literally anything is better than using environment variables. Thank you very much for watching. I really appreciate you getting this far, and I'll see you next time. Bye bye.